when studying springs, something comes to mind, which is conservation of energy. Now, when you are studying energy, typically when you get into the conservation of energy, you will most likely study the combination for mechanical energy, and that will be only kinetic energy, and then the gravitational potential energy. That's kind of the first step, and I can put up a link up above there. That's something that you probably would have been touching base in grade 11. Now, as you introduce springs and you have elastic energy, therefore you will start to notice that this mechanical energy is going to start to grow. And you can transfer various forms, okay, of energy from one form to another. So just as the law of conservation states, which is that energy cannot be created, it cannot be destroyed, it can only be transferred. Now, it can be transferred between the various forms of energy. Now, here is going to be an example where I'm going to show you how you can incorporate the elastic potential energy, so related to springs, and try to see how it conserves, okay, and then transfers to kinetic or potential energy. That's kind of going to be our goal. Now, what I would want you to also recall, so just as you can see there on the screen, so the M, okay, just stands for the total mechanical energy that you have, and it is all of the energies that are possible. So kinetic energy, gravitational potential energy. Now here I put EP, which is going to be the elastic potential energy. And then of course there are many other energies that it can transfer to. But typically as you're getting in, so from grade 11 and then you're jumping into grade 12 or introductory physics, you most likely are going to be dealing with these. And then as soon as you introduce elastic potential energy and springs, you can start to do a little bit more interesting examples. So my goal here is to show you one of these examples and then see how these conservations of energy can take shape. So here it is, okay? So here's the example that we're going to tackle. So it's a monster of an example, but it's a pretty decent one. And I'll put references back down below because I incorporated actually from the text, okay, of a grade 12 example, and then I kind of changed it up and then used the AI and ChatGPT to try to change the example for us. But here is a nice little healthcare example, and I'll walk us through it. So a patient is undergoing physical therapy using a compression device to strengthen their leg muscle. So they're basically just kind of pressing it in, okay, it has a spring and it compresses down. The device uses a spring mechanism, okay, to apply the force. The patient's leg is pressed against the compression device's spring with a constant of 325 newtons per meter. The spring is compressed by about 15 centimeters, so not that much, okay, from the equilibrium position. After being released, okay, from being compressed, the leg moves 4.5 kilograms, okay, mass, simulating a foot plate along a frictionless track, and then up a frictionless incline at a 45-degree angle. Okay, so let me just picture this for you and then see what actually is transpiring here. So imagine that you have some kind of a compression, okay, spring within here. So this is going to get compressed, okay, and it is attached. So here's some kind of a plate, okay, we're going to be attaching to this plate, and maybe I'll change it a different color. So you're going to have, okay, a particular device which is going to get compressed by the legs. And this compression, through this example, tells us that we have, okay, compressed this spring. So let's imagine that the spring, okay, is somewhere along here. This would have been your position 0. This is your equilibrium position. And then now it has been compressed, all right? And that compression that you see there is 15 centimeters. That's at least what they tell us in the question. So we've compressed this with our legs. And then we're going to let it go. And when we let it go, okay, so this particular kind of device which is holding down the spring, well, if you release the legs, okay, this is going to move. Now, how is this structured? Okay, so this is going to be on a surface, all right? So here's some kind of a surface that it has. And then that surface, okay, is going to, so just so that this doesn't keep flying off, okay, will start to incline. And it's telling us that the incline, okay, in here is 45 degrees. So therefore, this launches, okay, after it's being compressed. And then as it lets go, so obviously it will pick up speed, and then it's going to move up this ramp. And then of course it's going to stop at some particular point. So let's take a look and see how we can break all of this down. I'm going to just write down all of the information that they gave us. So we had a spring constant, that is 325 newtons per meter. That's already in metric standards. We have that this, okay, kind of a plate, okay, or device is 4.5 kilograms. That's what we know there. We're supposed to be rounding to 3 significant figures. All right, so we'll do that for our final answers. And we have an angle of 45 degrees, which I drew out. So we have all of this information. So for part A, let's take a look and see what they ask us. Determine the elastic potential energy stored in the spring before the patient's leg is released. Okay, so now what I would want to do is I'm going to steal this and I'm going to kind of copy it out and I'm going to bring this down. And I want to be able to explain what is going to be happening in terms of this law of conservation. And now we have introduced the springs. So because we have friction, now because we have no friction, okay, so this is all frictionless surfaces, we'll assume that there's no friction, there's no internal or external frictions at all in the spring, outside of the spring. So technically, we will not run into any other form of transferring energy. So for example, it will not go into thermal energy. So for example, no heat is going to get generated. It's just going to have these 3 forms. So if the plate gets released, it's going to move. So there's going to be kinetic energy. If it's going to go up the ramp, it's going to have gravitational potential energy. Now, again, so please remember that gravitational potential energy is always with regards to our reference point. So we're going to assume so that the height is equal to 0, and that height is going to be right here. So if it's sitting on this surface, it has 0 gravitational potential energy. So at this instant, as it gets compressed, it will have no gravitational potential energy. Also, if it gets compressed and gets held there, there is no speed, so there is no kinetic energy. So therefore, all of the mechanical energy is being stored in the elastic potential energy within the spring. Now, we know what that is. So a spring has 1/2, and it's going to be times K, multiplied by whatever it has been displaced. So I'm going to have that displacement right there, and it is squared. And this is coming from, okay, so if you want to be able to find out where this is, I'll put up a link up above there, okay, so that you recall this. All right, so now next. So what we have in here is all of this is given, so it's 1/2. This is 325. And our compression, so I have to be careful here, I'm going to change it back into meters to make it metric standard, and then you'll see that it's not going to be that much energy. All right, let's take out the calculator, and this is a measly 3.6, and I guess I'll round it off, although I'll keep it on the calculator there, so 3.66 joules of energy that would have been in the compressed form. So this is 3.65625 if we want to keep all of the decimal places. So I'll just leave it as it is for the moment. So that is the elastic potential energy. And now by the law of conservation, if this gets released, that energy is going to get transferred into one of these. At first, since it's going to be on the actual surface, it's going to be purely shifting over and moving to kinetic energy. And then as it starts to move up, it's going to have both kinetic energy and gravitational potential energy until it gets to some particular height, which is going to be the maximum height where all of this energy is going to get transferred into gravitational potential energy. And then it's going to stop there, and then it's going to slide back down. And if this was kind of a perpetual machine where there's the energy just gets transferred back and forth, this would have been just weaseling back and forth forever. All right. That's if there was no frictions or no change to any other form of energy. Okay, so now next, so part B. So within here, so calculate the speed of the foot plate as it travels along the horizontal track. So we want to now know, so as this gets released, right, what will be the actual speed that it picks up. So as it picks up, it's going to get all the kinetic energy, and that kinetic energy is going to transfer from the elastic potential energy. So this just gets transferred right into this. So with this, then we know that the kinetic energy is going to be equivalent to the elastic potential energy. There's no gravitational potential energy, at least not yet, because it's on the actual horizontal. So we know what this is. We've just calculated it. So I'm going to put 3 point. I'll actually, since I wrote it down, okay, so I'll keep all of these decimal places. And then my kinetic energy is just 1/2 mass v squared. Now, of course, I know what this is. So this is 1/2. My mass of that plate is 4.5 kilograms. And then I have v squared, which is my only unknown. So I can now rearrange this formula and solve it. There you have it. All right, so that is the actual speed. So it's moving at 1.27 meters. Sorry, this is per second, not second squared. That would be acceleration. So it's moving pretty quick. All right, so as it goes through on that frictionless surface. Now, for part C, it says determine how far up the incline, okay, so this will go. So this is going to be interesting because I'm going to just steal this incline in here. Let's duplicate it, bring it back down. So what exactly is going to happen here? Well, so that plate is going to get or be moving up this incline. Now it's going to get to a certain height. Now, what height is it going to get to? All right, so this particular height, so I'm going to write up the height. And now that height means that if you take all of the energy, so this is going to have, initially, it's going to have kinetic energy, so as it goes through. But now when it gets to here, so it still has only kinetic energy. But as it starts to move, it will have both kinetic energy and potential energy. And that kinetic energy is going to be transferring to the gravitational potential energy, right? So the spring releases that energy back in, and now it gets transferred until basically, eventually, that plate is going to stop moving. Where V is equal to 0, there's no more kinetic energy, and therefore all of it goes into gravitational potential energy. Now, for gravitational potential energy, we do know that our result is mass times gravity times whatever height, okay, that we have. But now here we have to be careful because this will be the actual height. Now, they're asking us for the distance on the ramp, right? So this is, I guess, is going to make this delta D, okay? So that would have been the distance that it goes up the ramp. But once we have this height, we can figure that out because we know this angle. So from that angle, we know that this is going to be sine of the angle, which is 45 degrees. And that is now why I'm picking sine, because it's opposite over hypotenuse, right? I will know what the opposite is, which is the height, which is the total height up. And I will find that through right there. And then I can find out what the delta D is just by rearranging this. Okay, so now let's take a look. So again, the total energy that we have in here, so that this is the total energy. I'm going to duplicate this back in. That is your gravitational potential energy, all right? So that is your gravitational potential energy. So all of that gets transferred in. Now your mass, so that's 4.5. The gravity, so 9.8 meters per second squared. And then this would be your height. That is our height. So keep in mind that's in meters, so it's about 8 centimeters. So it doesn't go very far. And now we can substitute this back into here and then find out our delta D, so which is the distance on the ramp that it goes in. So that would have been delta D, and then you can take your height, which is 0.08 to 9, etc., divided by sine of 45 degrees. There you have it. All right. So the idea behind this example isn't to trick you in any way. It is just to show you that now the law of conservation, as you keep learning about the various forms of energy, you can indeed transfer them all the way through, and you can come up and be pretty creative on the examples that you can set about. All right, so that is it for this video. Okay, I hope that you have found it useful. Thanks for watching. See you in a future one. Bye, everybody.